Today let me learn about how to implement your functions using other two level as well as the properties of your exclusive OR gate. Now in last class we implemented your functions using your NAND logic and NOR logic. So uncomplemented functions are implemented using your AND OR gates or OR AND gates or NAND or NOR. So the first gate represent your first level. So we use a set of AND gate. In the second level we are using your OR gate. So if your function is in SPOS form, so then it will be implemented using your OR and form or and non-degenerative form. So that means first level will have a set of OR gates. In the second level we have your AND gates. So now SSOP forms are implemented. After minimization it will be converted into SOP forms. So now those SOP forms are implemented using set of AND gates in the first level and a OR gate. So we converted SOP forms into NAND function, and POS forms is also implemented using NOR. And if you have a function which is complemented, uncomplemented ones are implemented using 1 to 4, and complemented functions are implemented using 5 to 8 non-degenerative forms. Now, so these non-degenerative forms are implemented using your AND or invert logic only. So now these two forms are said to be NAND, or we can also call this as a AND and NOR. So these both non-degenerative forms are implement the same functionality, but here the first level is having NAND gates and the second level is having AND. First level in your AND and NOR is first level have AND gate, in the second level we have OR gate. So both will perform your AND or invert functions only. And now, so let us take an example how to implement this function using your AND or invert and by replacing your AND and NOR gate. So now, so it's a complement function of SOP form. So since that we have a first array is having a AND gates, a set of AND gates. In the second level we have a OR gate. Since it is a complemented function, hence the output of this is complemented using a NOT gate. And if your output of your OR gate is complemented means, so you can replace with the symbol of NOR. Hence it comes to your non-degenerative form of AND NOR. So now if I replace this NOR with an inverted input and by just transferring these all the bubbles to the outputs of your first level, now first level will have a set of NAND gates, the second level we have your AND gate. So this will give you a functionality, whatever the functionality it will give, which is AB or of CD or of E whole bar is also implemented using a non-degenerative form of NAND and AND. So since we transferred your bubble to the outputs of your AND gate, so hence it become the NAND. The second level it will become AND. In the same manner, OR and invert implemented using OR NAND or NOR OR. So let us take the example F is equal to AR of B and of C or of D and of E whole bar, which is in the nature of POS, complement of your POS forms. So complement of POS form, first level we have OR gate, second level is a AND gate, and it's a complemented function, output function is complemented, hence we used a NOT gate. Now this becomes the NAND, and now this NAND gate is replaced with the bubble input OR. So if I replace with the bubble input OR, and these bubbles are transferred to the outputs of your each first level OR gates, then first level is converted into NOR gates, in the second level we have your OR gate. So implementation of your non-degenerative form of your complemented POS form is implemented using OR NAND, or it can also be implemented using a non-degenerative form of NOR OR, will give you the same functionality. Next, exclusive OR function. Your exclusive OR gate is a special type of gate in your logical gates. So where you are going to use this gates are used to implement your half adder, full adder or your subtractor, which are one of the examples of your combinational circuit. Let me learn about, so which is a 2 input exclusive OR gate. Its truth table we have it, and your output expression of your exclusive OR is complement your A bar B or of AB bar. So this is the Boolean expression of your exclusive OR gate. So where it will give you the logical one functionality for a different inputs on your AB. For similar inputs, so you have your logical 0 output. So what are the properties of your exclusive OR function? So these are some of the properties. It also obeys your commutative law, as A exclusive OR of B is equal to B exclusive OR of A. It also obeys your associative law, which is on three variables: A exclusive OR of B, exclusive OR of C is equal to A exclusive OR of B exclusive OR of C. So now identity or law is also proved using an exclusive OR function between your A exclusive OR of 0 will give you A exclusive OR of 1 is equal to A bar. So now, so let I have your equation A bar B plus AB bar is your actual output expression of your Boolean expression of your exclusive OR. Replace your B input with 0 and now B bar is 0 bar. So now here 0 is the A bar and of 0 is 0. A into 0 bar is 1, so which is equal to A. So hence A exclusive OR of 0 is equal to A. Now A exclusive OR of 1, it becomes A bar. So since your B value is 1, so A bar and of 1 plus A 1 bar. So A bar and of 1 is A bar plus A into 1 bar is 0. So hence it will give you, if you are one of the input of your exclusive OR is logic 1, it will give you complement. So it is also used as a NOT gate. So exclusive OR gate can function like a NOT gate. So when it act like a NOT gate is because one of the input, if you apply always with logical 1, so it will give you the output which is equal to complement of its connected input. So self inversion. So here A exclusive OR of A is equal to 0, A exclusive OR of A bar is equal to 1. So these are the 5 main properties of your exclusive OR gate. Now let me implement your exclusive OR gate using NAND gate. So we can implement your exclusive OR gate with using only minimum 4 number of NAND gates, as G1 is equal to is a NAND gate operation between your given inputs of AB. So it will give you the expression of AB bar, and G2 will give you the NAND operation between A input and AB bar. So now A into AB bar. Now using De Morgan's theorem, let me distribute this as sum of your complements of the variable as A bar or of B bar. So now here, now let I multiply this with A into A bar plus A into B bar. So as your A into A bar is 0, so hence the final expression for this is, so 0 plus AB bar whole bar, so which is equal to AB bar whole bar. Next G3 will have your two inputs, one from your AB bar, the other input from your B input. So hence it will give you the NAND operation between B and AB bar, which is equal to B into AB bar. Now the last gate will give you the output which is a exclusive OR function. So since the inputs which are connected to this is, so AB bar whole bar and of BA bar whole bar and operation between these two inputs, NAND operation between these two inputs. So here AB bar double bar using De Morgan's theorem, this AND become or B AND of A bar double bar. So these double bars are cancelled, then our output expression is AB bar or of B AND of A bar, which is a exclusive OR. So like this we are going to implement your exclusive OR using your only NAND gates. You can also implement using your NOR gates. So this is the expression for first gate. G1 is A OR of B whole bar. G2 will give you A OR of B bar whole bar. G3 will give you the output function of B OR of A bar whole bar. Now output of your G4 is equal to A OR of B whole bar or of B or of A bar, which is equal to, so here double complemented and this become AND. So now hence we have here we have here AND operation between these two. Next G5 is also there. So hence here, so this double complement, so G5 will give you the output functionality of your exclusive OR. So now like this, so we were going to implement your exclusive OR function using your NOR gates or your universal